In this video, we now turn our attention to the hydrolysis of esters under basic conditions. So recall that hydrolysis is when you take an ester, you react it with aqueous, either acid or base, depending on what the conditions are, and the product is that you get out the carboxylic acid plus the alcohol. Okay, so a couple of notes on this. First of all, if we're under basic conditions, to produce a carboxylic acid, H3O plus must be added at the end of the mechanism. If you just do the reaction with aqueous sodium hydroxide, the reaction will end at the carboxylate anion. And a word on the notation that I've used up here for the net reaction. So when you list two reagents over and under an arrow with a 1 and a 2, this implies that reagent 1 is added first and then reagent 2 is added second. They're not both present at the same time. Why? Because they are incompatible reagents. You have a strong acid and a strong base. They will react with each other in a neutralization reaction faster than either one of them could react with an ester. Okay, so let's look at this mechanism, at least to get us to the carboxylate anion. This is going to be a mechanism under basic conditions, so it's going to be the shorter of the mechanisms. So the first step, we have OH minus. It's a good nucleophile. It's a good enough nucleophile to attack the neutral ester. Okay, so hydroxide comes in, attacks the carbonyl carbon. That's one arrow. Break the CO pi bond. That's another arrow. And we end up with the tetrahedral intermediate with a minus charge on what was previously the carbonyl oxygen. Now the tetrahedral intermediate collapses to reform the carbonyl group, but now we kick off OR minus instead of OH minus as we regenerate the carbonyl group. Okay, so now you have a carboxylic acid, but you are under basic conditions. And under basic conditions means that favorable proton transfer reactions are faster than any other reaction imaginable, and there will be a favorable proton transfer reaction between the RO minus, the alkoxide that you just kicked off, or for that matter, any OH minus in solution, and the carboxylic acid. This reaction is favorable by 11 pKa units. So that's going to deprotonate the carboxylic acid, and you are going to end up with the carboxylate anion. If you want carboxylic acid back in a second step after all this is finished, you need to add acid to reform the carboxylic acid, which is frequently but not always done. So while we're on this topic, I would like to actually give you an application, and that is that hydrolysis of esters under basic conditions are frequently called saponification reactions. And the origin of this is this reaction is actually what is used to synthesize soap. Okay, so carboxylate anions, which is what you immediately get out of this reaction, are effective as soaps or detergents, especially if they have a long chain carboxylic alkyl group on the carboxylate. Why is this the case? Well, the reason you really need soap is to remove oils in the form of sweat or whatever comes out of your oil glands from the skin. But they cannot be removed from the skin using just water because they are not water soluble. Try washing your sweaty face with just water and you're still going to have that layer of grime on your face. Okay, so soap molecules, the carboxylate anions, are water soluble because of their charged head. Okay, the negative charge at the end, the hydrophilic polar group, whereas the grease, sweat, oil, is nonpolar and will dissolve in the nonpolar tail of the soap molecule. So soap molecules will render the grease and oils on your body water soluble so that they can be washed off. Okay, so how do we get soap? Well, natural fats that you get from any animal, plant source, tend to be in the form of triglycerides. That is a triester molecule made of 3 fatty acids, which are simply long-chain carboxylic acids, and a molecule of glycerol, which is chemistry speak for 1,2,3 propane triol. Okay, so soaps are synthesized industrially by simply hydrolyzing triglycerides, which have incredibly high natural abundance, using NaOH, and you get the carboxylate anions as the product. Okay, so an example of ester hydrolysis under basic conditions. In the next video then, we will finish with ester hydrolysis by looking at the mechanism under acidic conditions.